Okay, and welcome to the second of three of these little things. Um, I'd like to keep it under five, but realistically, we're going to go a little over. But this one shouldn't be too bad. This is really just about addition and subtraction, and you just need to kind of understand and define the different types of radioactivity. So, we need to discuss notation, because I know you've done this before and you've seen it, but just so you remember it. When you notate, the top number is the total mass of the atom, which is a combination of protons and neutrons. We do not factor in the mass of an electron because they are, it's just so small it doesn't make a difference. It would be like factoring in the weight of a nickel in terms of the weight of the Earth. Like you just don't bother with it. So the top number, so this is uranium. Uranium has a mass of 238, and it has a total of 92 protons, which is also the number of electrons. The protons and neutrons don't have to match, but the protons and electrons do, unless you have an ion, which we're not going to mess with. Okay, so the top number is your mass number, which is protons and neutrons, and the bottom number is your atomic number, which is the number of protons. This bottom number right here is what actually determines what element you're dealing with. If this is a 6, it's carbon. If this is a 10, it's neon, so on, so on, so on. That's what the difference is. There is something called an isotope. It is Springfield's baseball team in The Simpsons. But the reason they're called the isotopes is because of the nuclear power plant. An isotope is when you have the same element, but you have a different mass. This is a result of extra neutrons. So carbon is carbon because it has 6 protons. You see 6 right here. If I gave it 7, it would no longer be carbon. But I can change the number of neutrons. And if you change the mass of carbon, it becomes an isotope. Carbon normally is found 6 and 12. Mass of 12, 6 protons, 6 neutrons in the nucleus. However, it's also found with 14. It's quite common, actually, carbon-14. You've probably heard of carbon dating. Carbon dating is your bones have a certain percentage of the carbon in your bones is carbon-14. Over time, it decays. It emits particles and returns to the C612, just a regular old stable carbon. So by looking at how much of the carbon-14 has turned into carbon-12, we can tell how old something is, because we know exactly how long that takes. This is where our buddy Al comes in. His energy mass equivalence. In 1905, Albert Einstein publishes a second major theory called the energy mass equivalence in a paper called Does the Inertia of a Body Depend on Its Energy Content? I think we all know the answer to that, Al. This energy mass equivalence you recognize as E equals mc squared. Looking closely at Einstein's equation, we see that it postulated that the mass held an enormous amount of energy within itself. This is called the binding energy, or rest mass energy, as it is the energy that holds the atom together when it's at rest. The large amount of energy comes from the fact that the speed of light is squared. So if you look at this, even if you had 1 kilogram of mass, if you multiply it by 3 times 10 to the 8th, which is squared, that's enormous. Okay, that's 9 times 10 to the 16th joules of energy. That's an amazing amount of energy, and that's just 1 kilogram. If I could somehow break apart the bonds in just 1 kilogram of mass, I would have that much energy, and that's an amazing amount of energy. You can freeze this slide if you'd like to go back and kind of review all the different types of energy that we've done, just to make sure the units all match up, but they do. Now, there's something called the mass defect. The mass defect is, well, the universe is weird. When you put 2 things together, each having a mass of 1, you don't get something that has a mass of 2. Okay, so let's read through this one. The more stable the nucleus, the more energy needed to break it apart. Like if you wanted to break apart carbon-612, you would need much more energy to break that apart than an more unstable carbon-14, which makes sense. The energy you need to break apart a nucleus is called the binding energy, or the rest mass energy, if you remember. Einstein discovered that the mass of separated particles is actually greater than the mass of the intact, stable nucleus. That difference in mass is called the mass defect. So basically, if you have 2 things, each with a mass of 1, it doesn't equal 2, it equals 1.9. So for a long time, we had no idea where this went. It turns out That difference in mass, the mass defect, is basically the extra energy needed to keep. You wonder how protons are stuck together in the nucleus? Because plus charges should avoid each other. There's something called a strong nuclear force. It's one of the four fundamental forces. But you need energy to hold these things together. That little bit of mass, that 0.1 from the last problem, is turned into energy through. So it's turned into an enormous amount of energy, even though it's a tiny little bit of mass. That's turned into energy, and that's the energy that keeps the nucleus from exploding. So for instance, if you look over here, here's carbon. You see that carbon has 6 protons and 6 neutrons. Here's the mass of each. Remember, neutrons are a little bit heavier. So if we add them up, 6 of these and 6 of these, we get 12.096646. However, when we actually weigh this thing, we end up getting 11.996709 with a difference of 0.098937 AMU. AMU is atomic mass units. Well, it's not a huge difference, but it's a difference, and that's something that we really have to pay attention to. So there, if you want to pause it over here, here's helium-4. You can just check and see the defect on that. There's not much else on this screen for you. Okay, we're already at 6 minutes here. There was no way I was going to get it under 5, but we're more than halfway done. So when an unstable nucleus releases energy and particles, that's called radioactivity. So basically, when you hear radioactivity, what you need to think of is the nucleus of an atom is just so stressed out because it's not balanced, and it just kind of, it vibrates, and sooner or later, it is going to emit that nastiness that makes it unstable. So it can become more stable. So it's getting rid of the stuff it doesn't need. So basically, it can do this a couple ways. It can do this through, so the 3 ways it can do it is through alpha radiation, beta radiation, or gamma radiation. And each one's a little bit different. They're basically 4. The positron one, I kind of lump in with the beta because they're both essentially the same thing. The first type is called alpha radiation, and that's basically an entire helium nucleus. It's an actual nucleus of helium, no electrons, so it's not an atom of helium, but it's a helium nucleus is actually spit out, and that's called alpha radiation. Now, the second type is called beta radiation, or beta decay. So it can be called alpha decay also. It just means radiation. Beta is basically when an electron, which has no total mass, so that top number needs to be 0, but it has a charge of -1. So that is an electron. Notice the symbol for electron is just a lowercase e. Okay? Or sometimes you'll see an e with a little minus. That means electron also. The next one is positron, which is the same thing. It's an electron, but it's like it's twin. It's, instead of a negative charge, it's positive, and that's easy enough. The last one is called gamma. That's the really serious stuff. The symbol for that is gamma, letter C in the Greek alphabet. It just gets really kind of squished up when you type it, so it kind of looks like a Y if you look at it. It has no mass and it has no charge. This thing is just so high energy. That's the most energetic of radiation. So basically, the nucleus is unstable because it has too much energy, so it spits out energy. And you may also see from time to time just one proton or just a neutron being ejected also. But these are the 4 big ones. These are the 3 big ones. Okay? Alpha decay. This is usually the one, this is the most common of them. It's really just a matter of subtraction. So for instance, if you take, so if you look at what we have down here, you have plutonium, not PT, PT is platinum. So you have this element, plutonium, which has 94 protons and a total of 240 mass particles in its nucleus. So this is an unstable atom. Plutonium decays, that's what it does. So it's constantly in a state of these nuclei are constantly trying to become more stable. And a very stable place for them to be is with 236 neutrons and 92 protons. So what they do is they eject a helium atom. And they eject that helium atom so it can become more stable. But it really is a simple matter of addition. 236 plus 4 equals 240. So if you started with 240, and you emit a helium alpha, then you're going to drop to a mass of 236. That's really all there is to it. So this chemical looks like a chemical equation. This decay equation just shows you that it's really just a matter of addition and subtraction. One place you're going to find alpha decay is in your smoke detector. Smoke particles get in the way. So basically there's a detector and it's constantly americium, whatever. It decays. It's an alpha emitter, so it's constantly emitting these particles, and these particles fly across and are collected on the other side. Okay? But when there's smoke in the way, those particles now bounce off the smoke. And if they bounce off the smoke, the circuit is broken, the alarm sounds. That's why water vapor shouldn't set off your smoke detector, because it's just not big enough like smoke particles. Beta decay, once again, you can see the decay. 228, loses no mass, remains 228. If this thing emits an electron, it becomes more positive. So it goes from 88 to 89. So one of those neutrons actually turns into a proton. A neutron burps out an electron, and when it burps out an electron, it becomes a proton. Remember that difference between the mass of a proton and a neutron? Well, there's your difference. A positron is the same thing. Since there is no mass emitted, the mass remains the same. But if it burps out a positron, one of those neutrons, one of those protons burps out a positive charge, its positive charge, it becomes a neutron. So the atomic number actually goes down by 1 when it burps out a positron. You can pause this and read it if you want. Gamma decay, this one, everything stays the same, 240, 240, 94, 94, because the gamma ray has no discernible mass. It's high radiation. High energy radiation. This is the upper end of the electromagnetic spectrum, the opposite of radio. So it's gamma decay. An application of gamma rays, they're the most dangerous. So if you get hit with gamma rays, they're so high energy that they can kill your cells. They kill stuff inside your cells. They can used in CT scans, radiation therapy. It's why people's hair fall out when they go through chemo. It's because they're being shot with very high energy, and basically you're killing you're killing all the living cells, but you're trying to kill the cancer cells also. So it's kind of like take the good with the bad. And here's just a gamma ray X-ray of a truck, and then a couple real basic things. Most of these you're going to want to pause. These are very specific. Fusion. In terms of fusion, you have 2 elements, 2 hydrogen, and when they collide together, they have to be the right combination. You get 1 helium nucleus, and you get an extra neutron that's formed. And that's called nuclear fusion. That's what's going on in the sun right now. Once again, you can pause and read this if you'd like. And then the other type is something called fission. Now, you're not going to have to memorize this big, long thing at all. But basically, fission is where, these are the nuclear weapons you probably heard about in like World War II and everything, with chain reactions and things like that. Basically, we take a bunch of uranium and you shoot it with neutrons. And when you shoot it, you destabilize the nucleus. So here we shoot a uranium nucleus with a neutron, and it basically breaks up. But remember that mass defect from before, which meant that there was less mass. So that difference in mass now turns back into energy. And when you have a chain reaction, you can see 1 uranium breaks up into 2 different nuclei, which now will crash into more nuclei, which will make more nuclei, and you get that chain reaction, which releases a whole lot of energy. All right, that's it for number 2, and wow, way over. Sorry, guys.